All right, welcome to Training Data from CosmiQ, arguably the world's richest and most compelling data science podcast. In for our usual host, Ryan Lewis, today, I'm Nick Weir, a data scientist at CosmiQ, and today's episode is the third and final part of the three-part series with some of the great minds from Azavea, a certified B Corporation out of Philly focused on using geospatial tech and open source software to solve difficult problems across a variety of domains. In the studio today with me is Rob Emanuele, the VP of Research at Azavea. How's it going, Rob?
Pretty great. How you doing?
Great. And also here from Azavea, we have Joe Morrison. I don't actually even know what your title is. What is your title?
I change it depending on the audience, to be honest.
Okay. All right.
But I'm just a sales guy.
Okay. Joe, the sales guy. And then we've also got Jake Shermeyer, a research scientist at CosmiQ. How's it going?
Hey, good to be back. Last but not least.
That's right.
Debatable.
So today we're going to be talking about some recent work that Azavea has done to explore how to integrate some of the unique things that you get from geospatial data sets, such as multi-spectral imagery, elevation information, some other features that you don't get out of your classic images into computer vision models. So first, let's start out with the basics. Jake, I know in your past life as a geographer at USGS, you spent a ton of time looking at all kinds of imagery, including multispectral. So given that we're going to be talking about adding things like multispectral bands into models, can you tell us what multispectral is and what it gets used for?
Yeah, sure. So just kind of a history lesson on satellites. So some of the first Earth observation satellites were launched really in the late 70s. So one in particular that I find interesting is called AVHRR, which stands for Advanced Very High Resolution Radiometer. So could you guys guess what the resolution is on that, the spatial resolution? Very high resolution. It was 1.1 kilometer. So at the time that was considered advanced. Landsat 1 had also been launched, and that was around 90 meters. But when you don't really have this ultra-high spatial resolution, you need to kind of make up for that in some way, and that's where multispectral comes in. So you can have augment your feature space, so have more information about the things you're trying to detect by adding multispectral layers. So different types of layers here. We're talking about visible spectrum, so what our eyes can see, out to the near infrared, and then you could go further out into shortwave infrared, or you could go finer into the ultraviolet. So most of the present sensors today operate kind of in the visible to near infrared with a select few. So Landsat, Sentinel operating in the SWIR resolutions.
And so what additional things can you get from multispectral? What do people tend to use?
Yeah, so I think one of the main applications, at least to start, has certainly been land use classification, just being able to discriminate between different types of land cover types. That really is a helpful application for multispectral. If you think back on kind of the early machine learning techniques as well, these were often, you would just drill down through each pixel. You wouldn't account for the neighboring pixels. So therefore, that really helps you with multispectral. I'm able to discern that this is forest versus this is agriculture because I have so many different channels with a bunch of different features in them, and then use that to be able to discriminate between the land cover classes.
Cool. Yeah, really interesting. So multispectral, you've also got things like elevation layers that you can get from some sensors. And so the problem here, of course, is that most computer vision models were initially generated for things like natural scene photographs, or what we would see from a photo we'd take on our smartphone for detecting dogs, cats, whatever small animal pet you're interested in. Right. And so, Rob, your team recently did some work to try to explore how to integrate some of this geospatial specific data into a deep learning model or a computer vision model.
Sure. Yeah. So we've been working with remote sensing imagery for a while, and I think the efficacy of things like NDVI and NDWI for detecting things like vegetation and water really showcase the the way that the near infrared can bring out different land use classes, like you were saying. However, if you're starting to train a computer vision model, and you don't have a very large data set or a large amount of time that you want to train the model, what you would want to do is use pre-trained models, something like ImageNet, which is trained over millions of images for various, for classification tasks that has many different classes. That neural network has now learned, so many different features of imagery that are sort of like pre-baked. So usually with a neural network, if you're going to start from scratch, you start from like zero weights or randomly initialized weights inside the model. However, if you start bootstrapped with a network that can already do things like detect edges or detect circles, right? You can imagine like a crop circle kind of looks like a cat's eye. Is that a weird example? So you kind of start from a baseline of like already being able to see some things in the imagery. Then you can kind of get a head start on your training, and then do something where you're fine tuning the model to the specific task that you're after. So you might have remote sensing imagery that has multiple bands that you want to take advantage of, but these pre-trained models are out there that are already went through expensive training that can help you bootstrap. And if you don't have the time or the data set size to like kind of get to where ImageNet is from scratch, you start with ImageNet, and but that presents a problem because that's trained on 3 channels. So how does the network take into account the multispectral imagery? And without certain techniques, you really can't. So what you do is you just say, okay, that's great that you have more information in those bands, but we're not going to take advantage of them. We're just going to use RGB. So in the first competition, data set that Azavea participated in, which was semantic segmentation over Potsdam, Germany, which was a land use land cover classification. We did try training a model from scratch, a fully connected neural network that did the semantic segmentation, and then we also tried RGB, bootstrapped from ImageNet, and then we also tried IRRG, so just actually taking the infrared, the red, the green, and then feeding that 3-channel image through the network that was loaded with the weights of ImageNet, and the IRRG model ended up being the best fit. So what happens is you sort of a lot of people just disregard those extra bands because they're hard to take advantage of.
Yeah, and that's certainly something that we have seen in the SpaceNet challenges that we've run in the past. We will, I think in every challenge so far, we've released multispectral bands as well. And we rarely see participants in the challenges taking advantage of them in the models, even though this would, if you're going from a 3-band image to an 8-band image with a full multispectral collect from one of the worldview satellites, you're more than doubling the amount of information that you're passing to the model. It's interesting that the going into the weeds a little bit here, that the IRRG model using pre-trained weights was worked well.
Yeah.
Any thoughts?
I don't
on
know
that
if I have insights on why.
Yeah.
But that's what we found. It beat it out every time, the RGB model. So I think it really is just like those sets of initialized weights that you're using. You're not using sort of the higher level functions of it to be able to like detect colors, but it's really just the time it takes to train a model from zero to recognize like shapes and be able to kind of create those baseline features is just, it takes a long time. So unless you're willing to train on a large enough data set with enough varied shapes and everything. So, but also that infrared, one of the actually 2 of the classes, it was low vegetation and trees. So because infrared picks up vegetation so well, I think it just gave a stronger signal to be able to associate with that class, which apparently the blue channel was not as competitive, so it ended up working better.
Yeah, and I think the blue channel in general is just probably the least valuable channel in multispectral. imagery,
Sorry,
just because
Blue.
it gets washed out by the atmosphere mostly, and it's also it's just where it is in the EM spectrum. It's more similar to the red and green channel. So I think near infrared is probably going to add.
Blue is the weakest color.
Blue is the weakest color. Yes.
The one thing that you pointed out, just for some broader context too, that I think is a misconception about this work in machine learning generally, is that Moore's law has made computation and storage much cheaper over time. It's still pretty expensive to be able to do real cutting edge machine learning work, and so unless you have the resources of a Google or an Apple or an OpenAI, and literally you're spending millions of dollars a year on computation, then you're not going to be able to get to the state of the art results. That's why these pre-trained models are so exciting for smaller companies like ours. And so if we cannot find a way to get competitive results with off-the-shelf pre-trained models, we're never going to be able to put those things into practice for every new project that we do. So I think people think, oh yeah, it's like over time it gets really cheap to be able to train these things. Like, no, for people actually doing the work like us, and the blog post you referenced, we're trying to find ways to adapt these highly expensive pre-trained models to be able to take on more information or adapt their architecture so that we can take advantage of all the information we're being provided in multispectral imagery. We are not investing in our own cabinet of GPUs at the office to train them, although I think some people do take that approach. They're just kind of two different ways to tackle the same problem of like you're resource constrained, you're time constrained, but you still want to be able to do cutting edge work.
Yeah, that's super interesting point, and it's something that I want to put a pin in and come right back to in just a moment. But first, we'll just take a quick commercial break. CosmiQ and the SpaceNet partners are going to be at ICCV in Korea at the end of October. Jake, what are you looking forward to the most about Seoul?
I suppose the conference. I haven't really thought about this.
Apparently, what about Korean barbecue?
I am very interested in Korean barbecue. I live in Annandale, which is arguably the Korean barbecue capital of Northern Virginia. So I feel like I've had good experiences there.
So you'll have a good point of comparison.
Yes. Beyond that, I've heard there's a great military museum there. Some other good stuff to check out. So we'll see.
Cool. And what are we going to be doing at this ICCV conference, which is the International Conference on Computer Vision?
For sure. So we had a paper accepted in ICCV, which was this paper around SpaceNet 4 and the Atlanta data set. So we had 27 different look angles over Atlanta, and we released a paper regarding the data set and some of the baselines we created. Nick was the lead author. We collaborated on this with the Intel AI Lab. So we're really excited. We'll have a poster there. We can talk to everyone. Is there anything else I'm missing?
No, I think you've got it. Thanks a lot. And for listeners who aren't going to be at the conference, if you're interested in that paper, you can find it on Archive. Just search for SpaceNet MVOI. All right, back to the show. Cool. So something you just mentioned, Joe, was that it can be incredibly expensive to train a model from scratch, of course, and that you might need an enormous amount of computing resources to do all of the training and fine-tuning down to the absolute best model on a specific training data set. But there are a couple of different things that I think are interesting around that. One is it's actually something, and Jake can probably speak to this more than me, but something that we've explored a little bit. We actually don't see a huge difference in performance on overhead imagery data when we're working with a model that was pre-trained on ImageNet and then we essentially retrained to now work on geospatial data versus something that we're just training from scratch for an equivalent amount of time, say a couple days on a couple of GPUs. Is that consistent with your experience, Jake?
Yeah, I think so. I mean, a lot of the features in overhead imagery, particularly remote sensing imagery, so where you have a spatial resolution less than 30 centimeters, the features can be quite different than what we're accustomed to seeing in natural scene photos. So really the ultra high res, traditional photographs that you're seeing in these ImageNet data sets. So I think that plays a role. And I know there was a recent paper in CVPR that kind of stated similar findings, that really the pre-trained weights, if you're transitioning to a domain that's significantly different may not really be all that valuable. That said, I think it's probably worth trying because the computational overhead is so much more significant if you have to initialize from random or zero weights.
Yeah, absolutely. And it should also be stated that SpaceNet Challenge participants almost always start from ImageNet weights as well. And yet, but yet when we take their models and then retrain from scratch versus with the ImageNet weights, we don't necessarily see a huge difference in performance.
And that's on a single contest data set?
That's right. Yeah.
Okay. And then you said for like 3, like what's the resources put into it?
Yeah, we're training for, I don't know, something like 2 days on 2 Titan XP GPUs, for example.
Interesting. I think that might be, we usually train a lot shorter than that.
Yeah.
And on something like SpaceNet, there is a lot of imagery to train on. So in use cases where we have, clients that want to find things in their imagery and they might only have like 1,000, 2,000 examples, right? In not too many images. It gets to the point where like fine tuning is possible, but starting from scratch is just like not going to happen. So I would say we end up training. We see, and we've done some tests on this to see that the efficacy of the model, like the performance metrics, spike a lot faster. And in certain situations, we see that it does plateau at a higher accuracy level than other, random initialization, which would, train towards that same performance level, but take longer to get there and then peak off. But then again, like, spending a couple days on a GPU on a larger data set is like not usually the situation we find ourselves in. So I think it's just, different situations have different techniques.
I'm curious as well. I mean, one of the things that I see the R&D team at Azavea doing a lot is kind of throwing stuff at the wall. So you might have, one of the challenges of deep learning is that there are so many parameters to play with. And so we might say, all right, we're going to go with like the stock hyperparameters, we're going to pick these 10 variables and we're going to isolate for those 10 variables and we're going to train different models, which each of those things isolated. And then if there's like some that show big signal, maybe we combine the best and do that again. If we had to wait 2 days for each one of those things to complete, especially if you've got 2 GPUs so that you're constrained in the throughput, we wouldn't be able to run through those experiments as quickly. So I'm curious, from your standpoint, is it a problem for you when you have to wait that like interim time for those things to train, or is that a kind of different challenge that you're not necessarily faced with?
Yeah, that's a good point. And it's, I think in terms of the 2-day time frame, we're probably doing most of our hyperparameter tuning on some shorter training experiments, but which won't allow us to see the higher plateau that you might be able to get, for example. But we'll try to do all the tuning on some much shorter experiments, and then once we feel like we've nailed down hyperparameters, we'll kind of do the full training process. So that doesn't really limit our research pipeline, but we're also, as you mentioned, working with the pretty large SpaceNet data sets. Our training tends to be more on the SpaceNet scale, where we tend to give participants up to a week to train their models that they're giving us for the challenges. So
I think we can learn from you, because if you think about what you're describing, you're thinking about a mature machine learning project. So we're often at this nascent phase where we're kind of like trying to reduce the risk of doing machine learning projects, and therefore we're not doing the optimal thing, we're doing the minimum thing. But I can imagine as some of our projects mature in like a year from now, 2-3 years from now, when we have a SpaceNet size data set we've been able to aggregate over that time, we're going to probably want to change the way that we're working. So it's cool to hear you describe how you approach the problem, because maybe that'll look more like how some of our team members are approaching it in the future when we've got these, what we would consider luxurious data sets to work with.
Yeah, that's a great point, definitely. And I'm curious, so you've talked about ImageNet pre-trained models. Do you guys do any work with any models that were pre-trained on geospatial data, on overhead imagery, anything like that?
We have some models that were fine-tuned on more specific like geospatial data sets, and then we reuse that
Sure.
for other applications that are similar, like the cars overhead with context data set over Potsdam. We trained object detection model, which proves useful for doing other types of vehicular like detection in overhead imagery in higher resolution like aerial imagery. So that's really the only example. I know that there's I'm curious about your perspective on like are there any pre-trained models on SpaceNet or otherwise that have been released that people have been using effectively on multispectral?
Yeah, so kind of a sidebar here, but I used the CalC dataset and actually SpaceNet pre-trained model. So it was trained to detect buildings, and then we just did some retraining, and then it can suddenly detect cars. So although we're doing segmentation with a little GIS post-processing, you can kind of create some bounding boxes around them and have a quasi-detection network, even though it's semantic segmentation.
Where can listeners read about that?
You can read about that on the downlink. That's one of our, 500 blogs, but one of the more recent ones.
Great. Yeah, and in terms of including multispectral data, that's a great question. So from the SpaceNet challenges, there aren't a ton of pre-trained weights out there. That's something that we've started releasing just in the past couple months. With the Solaris code base, we've retrained some of the participants' models using as similar parameters as we can to what they used, and then and put those weights up in the SpaceNet dataset bucket on AWS S3 for free download.
Now, are those because the nice thing about ImageNet is it's been trained on basically every type of backbone network, ResNet 16, ResNet,
Right.
like it's sort of like widely available for whatever model or framework that you're using. Is there like kind of a specific architecture that you've released, or is there plans to sort of do that similar type of pre-trained on various backbone networks that can be loaded in?
So at this point, there are just 4 different backbone architectures. They're all UNets with different encoders. So ResNet 34, a DenseNet 121, a DenseNet 161, and the BGG16 encoder. So there's some work in our blog, the downlink, on how to do some very quick fine tuning. We were actually very pleasantly surprised you could fine tune for 3 epochs of training, 5 minutes on the smallest AWS GPU instance, and take a model that identifies buildings in Atlanta, and suddenly now it works at SpaceNet Challenge winning quality in Khartoum.
Wow.
So we're hopeful that these kinds of pre-trained models for geospatial will then provide some value. But absolutely, doing some quick training from ImageNet weights makes a lot of sense to try to accelerate your pipeline, and hopefully having people take these weights and work with them, whether it's within the Solaris framework or not, will make it even faster for people to explore things like this.
It makes intuitive sense that something trained on satellite imagery that's then transferred to another task on satellite imagery that takes advantage of the full spectrum of the image as opposed to just a piece of it would be much more effective out of the gate. That's been a dream of ours to see that come to fruition for a long time, or I wouldn't even call it a dream. It's just sort of a given that someone's going to do that at some point, and it really hasn't happened as quickly as we thought. So yeah, if you're listening to this podcast and you're bored at Microsoft and you've got, a bunch of resources available to you, or you're at Google or Apple and you have a 10% time project you want to work on, you could do the world a service by releasing that type of a project. We would all be the first in line to take advantage of it.
Jake, have we done any work with comparing the performance models trained on just your classic RGB versus the full 8-band multispectral? Because the models that I was just describing, I should say, the pre-trained weights are either on RGB or RGB with just a near IR pan sharpened band added in.
So this research is a little dated, but I think Adam Fennett, and our colleague, led this a year or so ago, where he investigated if just what Nick described. So does RGB help, or does the 8-channel multispectral help from the Worldview 3 satellite when you're doing building segmentation? And his findings were really that the multispectral wasn't that valuable for this application. That's not to say that it's not valuable. It's just I think that when you're working with this specific type of multispectral, so we're just going from the visible to the near infrared in 8 channels. There's really a lot of overlap in those bands. A lot of the channels are really similar to one another, so you're not getting all that much more information. So when you're using deep learning to segment out buildings, you're really just looking for kind of shapes and textures and corners, specific patterns, and you're additionally not going to look for things like vegetation, where near infrared might be helpful. I think that the multispectral may have limited usage, and that's kind of what his results showed from one of those blogs.
I love that you said this research might be dated. It's a year old.
Yeah, it might be more like 2 years old.
It's the computer vision community at this point, I feel like.
Yes.
Yeah, we were actually testing building segmentation on SpaceNet Vegas with the multi-spectral approach, and I don't want to be speaking either, because I think it was RGB. Yes, it was RGB against full 8-band with the ImageNet pre-trained, and given we didn't try to optimize each of the models, but we were seeing maybe like a 0.02 F1 score increase, so not significant. In roads, we didn't see anything. But then, for other applications where it is vegetation or water, we were seeing a lot of difference. So I think it really varies between, what you're detecting and what sort of, there was another set of research that James McLean did around mutual information, detecting the mutual information between pixels and how much more information are these, does it really contain? And we were sort of convinced that, there's definite new information being, you can't predict certain band information from just subsets of the others. So, it's interesting to hear that there was not really a significant increase in buildings, because we thought we had identified that as a potential. But what you said kind of intuitively makes sense of it's more about the shapes and detecting the outlines.
That's one of the big fears we have when we're investing in research like this, is that, and you see this in the competitions too, is that, in the first week we can get to within, 0.1 of the leading candidate, and then we might spend 3 months to make up a few tenths of a point on the evaluation. It's just like diminishing returns in deep learning are everywhere. So there's some piece of me that thinks, oh yeah, the multispectral stuff, it's so intuitive that if you have way more information, you should be able to extract way more, but it may just be another subset of, or a special case of the idea of diminishing returns and doing a bunch of manual extra work to try to tweak these pretty good off-the-shelf models.
Yeah, that makes sense. So I think one more question that I'll open up to the three of you guys before we close out. What about potential drawbacks for using these pre-trained models? Are there any? I can't think of anything off the top of my head, really, so I'm not necessarily expecting anything, but can you guys think of any issues with using these pre-trained models for geospatial?
The only fear that I would have is just a little bit of an assumption about what works. Like you kind of see something that improved a model performance at some time, and then you just kind of keep going forward with that expectation of okay, I always need to do this in order for this to be effective. So when you had mentioned, actually we didn't see any difference between pre-trained and non pre-trained. That's that's an assumption that we've kind of established internally that we need to check. So I think the danger is to kind of say, okay, we always need to do this. We can't actually, work with an architecture that the pre-trained model won't fit into, because we need the pre-trained model, sort of, a supposed reliance on it, which may or may not be give you a more effective outcome.
Yeah, the fear that I have, I almost don't want to say, but the fear that I have is that everything we're doing is technically illegal in a case that hasn't been settled yet, because the licenses to the images in ImageNet are not owned by the people that build those pre-trained models. I mean, let's be honest though.
That's a great point. And
Yeah, it is.
every single company that's doing computer vision work is using models pre-trained on ImageNet.
And that data set may, in a court decision in the future, they may say, look, you don't have the right to use this in a commercial or even like in a research setting. That's one thing I worry about. The other thing I worry about is that we get really close to having super clean, legally speaking, data sets that we can start from, like SpaceNet, but then they're not licensed liberally enough that you can use them in a commercial setting. And therefore, if you're being really rigid about it, you can't make that final step to applying it. And so it doesn't stop the research community or the commercial community from building stuff and trying stuff. And I'm sure that will all get figured out in some way or another. Some hero will come in and provide the ImageNet replacement that's just as large, that's totally legally clean. But it does kind of amaze me how, I guess, cavalier the deep learning community is, both around ethics and around the intellectual property of what's happening. People like Google have like patented autoencoders and crazy stuff like that. I think because they want to prevent patent trolls from stepping in. But I do wonder if we're living in this kind of Wild West time where there's a bunch of innovation, and then eventually once this stuff just becomes mundane tools that people are using, it's going to get really constricted, and there's going to be a lot of legal quandaries that people wind up in.
Is that another Joe Morrison 3-year prediction?
No, that's like a 30-year prediction. Like if we get to the point where people care enough to sue and take stuff to court, that's a great sign. That means that it's been really adopted, and someone's like, oh, I see an angle here. Because if you look at what's in ImageNet, it's like pictures of people's backyards and of street scenes, and it would take a real stickler to be like, oh yeah, that crappy cell phone picture I took of my cat should not have been used as one of a million other examples in a model that was released. It just seems unlikely to me, but I don't know. Maybe that could happen.
Yeah, and I just say, as far as like the deep learning community, research community, like being cavalier, like, okay, we're gonna just move forward with this, and we're really gonna, we're gonna move forward with this. We're gonna use ImageNet, and we're just gonna publish our papers out in the open, and we're going to build open source software, and we're going to release open data sets. It might be legally unsound in certain ways, but I think it's actually revolutionary. Like the way Archive has just put out research in a way that, I don't have a background in deep learning. Like I don't have an advanced degree in computer science, but I read research papers and learn so much from the open source community, open publishing community. And then, SpaceNet is a great example of like, okay, there's this thing called ImageNet, like it already exists out there. So let's create something to seed the geospatial machine learning space and, really cultivate this open community. And it's just, it's really exciting. So, I encourage that type of Wild Westness because I flourish in it. Yeah.
Well, I think that's a great place for us to cut off. So I hope my voice as the host here has not been too sharp of a contrast from Ryan's usual dulcet tones, but let's be honest, at least you're spared from his usual pretty lame jokes. If you've made it this far, congratulations. You're now a geospatial multi-spectral deep learning expert. So thanks a lot to Rob and Joe from Azavea for joining us. Definitely check out their blog for the blog post that we were referring to around using additional bands from geospatial data, working with pre-trained ImageNet weights, and check out our blog for some of our work in related areas. Make sure to rate and review and subscribe to this podcast wherever you listen. And thanks a lot, and we'll talk to you soon.